we talked in the last video about autoencoders. Now we're going to talk about VAEs, variational autoencoders, which are kind of, they're very, very cool. They're very interesting to learn about, so hopefully you enjoy it. Now, VAEs are generative models, which means they can create new data. So not new data, sorry, they can create new of whatever we're looking for. So I'll give you the example. In the example before with animals, right? Before we could only create we could only recreate the exact animals that we had put into the encoder. So if we had sampled your cat named Billy, we could only recreate that cat named Billy. We couldn't recreate any new cat or generate any new cat images or new dog images. So that's what we're going for with the VAE. To do this, we learn the distribution of the data and then we sample from it. Okay? So we have some distribution of our data. So let's say, okay, P real of X is the distribution of our data. So this means that P real of X is the probability of a data point X being in, like the actual probability of it being in the data set. Let's say our distribution looks like this. I don't know, for these 1, 2, 3, 4, 5, 6, 7. For these 7 data points, it looks like this, right? We are going to try and learn a P of X that can match this as well as possible, okay? It's not just going to match it, it's going to fill in the space in between, okay? And that way, we not just learn the distribution for the exact points, but we learn the surrounding distribution. We learn the overall space, okay? And so to do this in an autoencoder, we're going to have to deal with, again, our high dimensional space X and our low dimensional space Z, okay? So in our X, we have some Px, the probability, so Px already here, okay, is the probability of observing a data point X. And remember, if we're looking to build this VAE for images of animals, our data point X, those are all going to be images of animals. So ideally, the big idea is we want to maximize this. We want to maximize P of X because P of X is telling us that when we put in a given X, what the output is going to be the probability of that X occurring. And because all of our X's are data points, right, we want to learn our P of X to be good and to be a good representation of the data. So we want it to be high for all of our X's that we input. Okay, so here's the goal. We need to maximize P of X. Okay, so before we do that, let's first consider the overall scenario that we have here, which is that we have our high dimensional space, but we also have our latent space, right? And so to go from a high dimensional to a low dimensional space, that is the encoding step, right? That's what the encoder does. It learns a distribution. It has to deal with the distribution of the probability of Z given X. Given a specific input, what is the best compressed version of it, latent representation of it? And then we, in the same way, have to be able to work backwards. And given a Z, you have to give me the X representation, right? Given this compressed form, how can I recreate what was originally there before? And then in the same way, we also have PZ here, which is just like PX. P of X is the distribution over the high dimensional space. P of Z is the distribution over the low dimension, latent dimensional space. It's what our latent space looks like. Okay? So again, this is very abstract. Our PX could look like some, weird swiggle. This could be what PX looks like, P of X, and P of Z could look like some even weirder squiggle. Okay? But remember, what's the idea here? The idea here is before in an autoencoder, remember we had this drawing, right? Where you had, here's your high dimensional space. So here's X. Here's your X space. Let's call it that. And here's your Z space. And we would take a point in here and we would map it to its latent representation. And we take another point and we map it to its latent representation. So I'll do a few of them. Ideally, I would color code this, but I don't want to take the time to do that. Hopefully you guys are getting the idea. Okay, and let's do one more. Map view to here. Okay. What we're going to do in the VAE that will be different is we're not going to map each x to a specific point in the z. We're going to map it to a distribution. So we're going to say for each x, whatever this image may be initially, just I always like to think of the example as images. Whatever this image may be, we're not going to map it to a point, but we're going to map it to some distribution. Each one of these is going to be a distribution. And you can already tell, right, as we fill this up with distributions, that's the first thing we do. The second thing we do is we restrict this latent space to be around a certain distribution. And we'll get into the math of all of this in a second. But we're saying that, look, our latent space needs to look like this. And these individual pools, so we have a big pool, which is the entire latent space, P of z. And then we have these little pools inside, which are being sent by, which are being, they're coming from a specific data point. Okay? So now, let's say this was a cat, this was a dog, this was a cow, and this was a giraffe. Okay? Now, obviously, if I pick this exact point right here, I'll get my cat out. But if I sample points around here, I'll get something that looks like the original cat, but is maybe another type of cat, a cat with a different, fur color or, of a different size. Same thing with a dog. Here, I'll sample and I'll get dogs. Now, what's interesting is that if, we restrict well and we make sure that our distributions cover the whole space, so these little pools, if they can cover the whole space, then even in between here, when we sample, we can get some meaningful results. Maybe if we sample in between a cat and a dog, we get some breed. An image that looks like a cat mixed with a dog. Okay? So this is kind of the power of VAEs, and this is how we're going to generate data using VAEs. So this idea is always a very good idea to keep in your head, that the overall PX is the distribution here. We don't understand that. It's too high dimensional, right? It's very high dimensional. Instead, we shift to the Z world and we restrict P of Z to be something nice and clean, and we'll talk about what we choose usually. Then each of these distributions fall inside of this P of Z and end up filling up the whole space. So we'd have another distribution here, would fill here, would fill here, right? They'd overlap. That's great. We don't mind them overlapping because it will learn what overlap means. Okay. Another example is you can imagine that these are all images. So this is an image of a 1 being sent to here, an image of a 2 being sent to here. Then if you sample, you can generate, like if you sample between a point between a 1 and a 4, I don't know, you might get some weird cross of a 1 and a 4, however you can imagine that looking like. Okay, so very cool stuff. We will go into the math into the next video, which is the best part, so stay tuned.